Hi everyone. So this video is going to be about torque. So the definition of torque is just a measure of how much force causes an object to rotate. So this is kind of like the rotational analog of force. Remember how we talked about how there's analogs between linear variables and rotational variables? This is rotation's force, torque. Now what happens here is an object is going to rotate about an axis O. So this can be, something like a disc or something like that. This would be our axis O right here. There's also an example of this wrench right here. This bolt would be the axis that this object is rotating around. You can also have just a particle that is just not even rotating really, and we'll get to that a little bit later. But as long as we have a specified axis and then a specified location where we're kind of measuring where this force is happening, then we have a torque that is happening. Now, the distance from the pivot point to the perpendicular force vector is called a moment arm, and we define that by little r. Kind of like a radius almost, like say if, again, we have like a disc or a sphere or something like that, and we have a force happening at the edge, our moment arm would be our r vector. Or radius in that case. Now for this, it is a specific definition that this has to be from the pivot point to a perpendicular force vector, meaning the force is coming in here perpendicularly, is that a word? And then here is our axis of rotation, and that moment arm, this R right here, this is perpendicular to that force. Now, sometimes the force is not perpendicular. So we would then find the perpendicular force component, because that would be the component that is causing the torque. And then R, in that case, would be our moment arm. But technically, if that force is not coming in at a perpendicular right angle to the axis of rotation or to the moment arm, then we don't actually call it a moment arm. It's not a huge deal. Now here's a torque equation right here. You can see the symbol for torque. That is written as tau. Well, that's a symbol. That's what it looks like. You'll see how I write it. I write it a little bit differently. It's kind of hard to draw, but this is the Greek letter tau, T-A-O. And our equation for this is R, our moment arm, times F sine theta, where F sine theta is our perpendicular force vector to that moment arm. So you'll see here, if we have a force that is not perpendicular to this moment arm R, then the sine component of that force, so here's our angle phi really here, and this would be the sine component of that force. So this is why we want this force right here, because it's perpendicular to that moment arm and it's giving the maximum amount of torque. That component gives the torque. So the torque equation, we call this a cross product, and I'll go into greater detail about what a cross product is in my next video. But basically, a cross product is when vectors, the force vector and the moment arm vector, F and R, are perpendicular to each other. So remember, a dot product is when two things are parallel to one another. So work was a dot product because we know that the maximum amount of work was done when force was parallel to displacement. Here, the maximum amount of torque is done when force is perpendicular to our moment arm R. So what's happening here is we want the perpendicular vector, which is why we use the sign in this equation here. Now, F sub R, we call this the radial component of the force. This is not going to do any, put any torque on this object. So it's like if you had something like this that can rotate and say that I'm trying to just, at this point, apply either an inward force or pull it outward, it's not going to rotate this object at all, right? Because it's just radially pushing inward or pulling outward. It's not going to rotate. But when we have our tangential component, F sub t, and say that is perpendicular to that moment, or just to the moment arm R, if that's perpendicular, you get the maximum amount of force, okay? And this is F sine theta. That's why we use the sine component. That's why this is a cross product. So we want that tangential force. Now that little r, like I said before, this is the moment arm to F sub t, our tangential component of the force. And the unit for torque is newtons times meters. Now this might look a little bit familiar because we know that work is force times displacement times the cosine of theta. So newtons times meters is what the work unit is made up of. But the important part here is that they're not exactly the same, okay? We don't remember, work is actually measured in joules. We don't measure torque in joules because we want to think of torque more like a force, okay? We don't want to think of it as energy like work is. So torque is never measured in joules. It's only measured in Newton times meters. Now in this whole the definition of torque, this is all from chapter 10. Now in chapter 11, we revisit torque in your book. And basically the only reason we revisit it is we are going to expand the definition now to apply it to an individual particle that moves along any path relative to a fixed point rather than a fixed axis. So we're just expanding this definition. I wanted to go over this now because it doesn't really even deserve a whole video because it's the same exact equation. But now we just have any individual particle as long as you are referencing a, axis point. And that's your fixed point. And it doesn't even have to be an axis. You don't even have to be rotating around that axis. The path, like I said, you don't need to be rotating. It doesn't need to be a circle, but we can still say that object has a torque about that fixed point. Kind of weird, but that's our definition of torque. So here, torque is a vector that can have any direction, and it's acting on this particle relative to a fixed point, and we call that fixed point O. Doesn't really matter. Same equation here. This is written in the cross product notation. So we have torque is equal to R, our moment arm, cross F. So R cross F. And remember, just like the dot product when we talked about work, it does matter the direction that you say these are in. So this is R cross F, not F cross R, because this has to do with the direction of the resultant vector, which is torque. And of course, another way to write this is RF sine theta. Sine theta is used because it is a cross product. And then, so these equations hold where F acts on a particle and the particle's relative position to the origin O is given by position vector R. I'll have an example of this in a separate video. Again, it's kind of a weird concept that we're not actually even rotating, so it's not like a rotational axis. So it's just a particle, you're measuring a force on that particle, and you have a relative point, a relative position given by, R, and you're measuring that position relative to origin O. And remember this angle right here, and I don't know if I said this on the last slide, but that angle is really important, that it's always between the R vector and the force vector, okay? So that's very, very important that we look at where those vectors are pointed, and the angle will always be in between those things. And we'll do some examples too for it to make more sense. Now let's talk a little bit about the direction of torque. Now, just like we talked about in rotation, we always know that counterclockwise is positive. So if the torque causes a counterclockwise rotation, it's a positive torque. If the torque causes a clockwise rotation, it's a negative torque. And this is really important, especially when we start doing equilibrium problems. You'll have different torques, different forces and different torques all over the place, and you have to, denote some as positive, some as negative. Now, this is exactly how we do with forces, right? In free body body diagram. So you have to denote one direction as positive, one direction is negative, and here counterclockwise is positive, clockwise is negative. Now we can get the direction of torque by something called the right hand rule. So what we do here with the right hand rule is we point our fingers in the direction of R, our moment arm. So here you can see that R is pointed kind of outwards toward us. And then 2, you curl your fingers in the direction of the force. And then 3, your thumb will point in the direction of torque. So this is my right hand. I don't know if it looks like it in the video or not, because sometimes these are mirrored. But say I have this object here, and to you, this would be clockwise. So that would be a negative torque. I think that's what it is. I'm sorry if it's backwards. But say I put my moment arm, so it would be R. So that would be like here. And then if I had my fingers are going to curl in the direction of the force. So say that my force is this way, and then my thumb would point into this object. So that's where we would draw the direction of the torque. Again, here you would point your fingers in the direction of the moment arm, curl your fingers in the direction of the force, and your thumb points in the direction of the torque. And you can see that in this picture as well. So again, a positive torque is counterclockwise rotation and negative torque is clockwise rotation. Now, just like forces cause accelerations, torque causes angular acceleration. So again, remember, this is the angular analog or rotational analog of our linear force variable. So we know that force is equal to mass times acceleration. So if we kind of translate that into our angular form, we get torque, or our net torque is equal to our I, which is our rotational inertia, times our angular acceleration alpha. So remember, we know from Newton's second law that force is equal to mass times acceleration. Again, torque is like your force analog. Remember, our rotational inertia is mass analog, and then of course angular acceleration is the analog for just linear acceleration. So this equation right here can just be translated from this Newton's second law equation if you can't remember it. So this is Newton's second law in terms of rotation. Now you'll see a lot of the time we're going to use this equation and the equation RF sine theta, that cross product or definition of torque. We'll use them in conjunction with one another. And we'll do a bunch of examples for this, so it makes a lot of sense to you guys.